Hello, everyone. Welcome to the webinar series on Rate Splitting Multiple Access 2021, organized by ComSoc WTC Special Interest Group on RSMA. So this is our sixth webinar, and it's our great honor today to have Professor Rodrigo C. Lamare from University of York and the Pontifical Catholic University of Rio de Janeiro as our distinguished guest speaker. So please allow me to make a brief introduction of Professor Lamare. Professor Lamare received his diploma from the Federal University of Rio de Janeiro in 1998. He received his master and PhD degrees from Pontifical Catholic University of Rio de Janeiro in 2001 and 2004, respectively. Since January 2006, he has been with the Communications Group, Department of Electronic Engineering, University of York. He's now a full professor of University of York. And since April 2013, he has also been a full professor at Pontifical Catholic University of Rio de Janeiro. Professor Lamare is a senior member of IEEE and an elected member of the IEEE Signal Processing for Communications and Networking Committee. He served as editor for IEEE Wireless Communication Letters and IEEE Transactions on Communications. His research interests lie in communications and signal processing. And he has published over 450 papers in international journals and conferences. So before the talk, I would like to remind the rules of our webinar. During the 15-minute talk, please keep yourself muted and you can type your question in the chat box. After the talk, we will have a 10-minute Q&A session. You can unmute yourself to raise questions, or I will choose 2 to 5 questions from the chat box. Okay, enjoy the talk. Let me stop sharing. Okay, Professor, you can share your screen now.
Lina, thank you very much for the introduction. Let me go to the slides. Can you all see the slides now?
Yes, but it's not full screened.
Just a moment. What about now?
Yeah, perfect.
Great. So, okay, thank you very much for the introduction again. And so this talk is entitled Precoding and Resource Allocation for Rate Splitting Based Multiple Antenna Systems. This is joint work with Andre Flores, Bruno Klugs, and Kumar Vijay Mishra. And I'm with the Pontifical Catholic University of Rio de Janeiro in Brazil, and with the Communications Research Group at the University of York in the UK. This is the outline of the talk. Okay, I'm going to start with an introduction to the topic. Then I'm going to move on to a system model of a multiple antenna system with rate splitting. Then I'm going to detail the precoding and stream combining techniques that we have developed in the last couple of years. Then I'm going to move on to power allocation, and I'm going to describe some power allocation techniques and something that we have done recently that I think is interesting. And then I'm going to talk about a very recent topic that we have started working, and we have some preliminary results, which is cell-free schemes with rate splitting. And then I'm going to wrap up the presentation with some conclusions and ongoing work. So, multiple access techniques are central to modern wireless networks. Most techniques that have been investigated recently, such as SDMA, NOMA, are susceptible to imperfect CSIT, channel state information at the transmit side. So it is in this context that rate splitting arises as a very powerful and effective solution that can deal with imperfect CSIT by treating interference and noise in a balanced way. So specifically, rate splitting can offer robustness against imperfect CSIT and increase the sum rate of wireless networks. So in the context of 6G networks, rate splitting will naturally be considered with multiple antenna techniques. And it is this, in this context that we are focusing our research efforts. So key problems that remain with rate splitting with multiple antenna systems include the appropriate ways of processing multiple streams for multiple antenna devices, which can be addressed by stream combiners. And precoding techniques for rate splitting based systems must be also designed carefully to obtain the expected advantages in terms of sum rate performance. And the third key problem or key point that should be taken into account is the resource allocation, especially in terms of power. This is key in rate splitting schemes to deliver its advantages. And one limitation of the current approaches is that they are costly and they are not inherently robust against the imperfect or imperfect knowledge of key parameters. So it's these problems that we are focusing on, and the contributions that I'm going to describe here include the block diagonalization type linear precoders and Thomson-Harashima type precoders for rate splitting. I'm going to also talk about stream combining techniques based on maximum ratio combining, min-max, and MMSC criteria. They are approaches to improve the sum rate performance and to enhance the quality of the common rates. And this is key for any approach that we might want to consider for devices equipped with multiple antennas. Then I'm going to also describe robust and adaptive power allocation techniques for rate splitting schemes. And at last but not least, I'm going to describe some initial ideas on cell-free schemes with rate split. So let's consider now the model of the system that we are interested. So in this model, we have basically one cell with a base station equipped with MT antennas, okay? And we have capital K devices. We're going to assume that these devices here, they're users, also known as users, they are all equipped with MK antennas, okay? So basically, at the base station, we're going to process a vector of symbols that are going to be obtained by the following procedure. We have K users, and these K users have K messages. These messages are going to be split, and they're going to be combined in order to form a common message here, okay? And we also have private messages associated with the K users. These messages will be encoded. They're going to be forming symbols. So we have here a common symbol here on top, SC, and we have the private symbols associated with potentially with the K users. And these symbols will be precoded using MT antennas at the base station. Typically, these MT antennas will be a number of is in excess of the number of users. if we're talking about large-scale multiple antenna systems, we're going to have a substantial number of transmit antennas, a much larger number than the number of users. Okay, so the excess number of antennas will be significant in the case of large-scale systems. And so this precoder here will be basically a transformation that I define as a function of P that will be applied to the symbol vector containing the common symbols and the private symbols. Okay. And this transformation will be applied, and then we have this effect of the precoder that will be mitigating interference. And at the receiver of a given user, we can have string combining, okay, because this is key to enhancing the quality of the common rate, okay, and the common symbols that will be used. And then this common symbol will be considered by successive interference cancellation decoding. So the better we have the quality of the common symbol, the better will be the SIG decoding. And this is key for our purpose here. And then at the end, we have an estimate of the message of the cave user of interest here. Okay, so that's the context of that will be describing most of the techniques. So precoding and string combining. So precoding, of course, is key to mitigating interference and enhancing the sum rate of multiple antenna systems. Linear precoders include the known, or very well known, zero forcing and MMSE techniques based on channel inversion, as well as block diagonalization approaches that outperform the former. Okay. So block diagonalization type precoders are known to outperform the channel inversion techniques, and they have been described in the context of rate splitting in this paper here at the bottom of the slide. And this is what we're going to describe here. That's the first time it was integrated with rate splitting, and we're going to show that they can obtain very substantial improvements in sum rate performance as compared to the zero forcing and MMSE linear precoders. In addition, Thomson-Harashima precoders integrated with rate splitting can also improve the sum rate performance, and they can outperform all linear precoders, including the block diagonalization type precoders. We're going to describe them later on, okay, after the BD precoders. So in multiple antenna devices operating with rate splitting, the data streams include the common and the private messages and common and private symbols. So our task here will be to increase or to improve the conditions of the common stream, because that's going to have a positive effect on the overall sum rate performance. SIG decoding will be used to remove the common stream that is known to all users. Okay, so in the block diagram here, we can see that this is a block diagram of the SIG decoding at the desired user. Okay, so we have here this WK is the string combiner, so it's a filter, okay, that is aimed at improving the common rate, which is then used for interference cancellation here. Okay. So that's the key idea behind common string combiner, and followed by SIG decoding. And we're going to consider 3 different criteria for designing this combiner here, WK. Maximum ratio combining, which is reminiscent of the idea of maximum ratio combining. It's similar, but applied to string combining. We also have one criterion called min-max, and we have the MMSC combiner. All the three will be considered for string combining. I'm going to show you what happens with them. The MMSC combiner, I'm going to show more details about this one, is basically coming from this formulation here that we try to minimize the mean squared error involving the common symbol and the result of the combiner and the received signal at user K. Solving this optimization problem here results in this expression that you have, it's like a Wiener filter, okay, involving the channel for user K, this cross-correlation vector here of the common string, and the covariance matrix of the received signal at user K. And the associated signal to interference plus noise ratio is expressed by this this expression here, this large expression. So that's the SINR of this particular common string. And the rate associated with the precoder and the string combiner for user K is given by this expression. This is for the common string, okay? And the ergodic sum rate that involves the common string and the private streams. The private streams is the second term here. This is the ultimate performance measure that we're going to use to show the difference in performance of the compared techniques. This is given by this expression here. This is the ultimate performance measure that we're going to show in all the simulations here that I'm going to illustrate. So, so the linear precoders with string combining, as a system point of view, they're going to do the following. We have the message splitting, the message combining, and the encoding, the symbols here, the common symbol, the private symbols, the precoding, and here we have the users. So I have described already the combiners, and now I'm going to describe the design of the regularized block diagonalization precoder. And this design involves solving the following optimization problem, and that we have the precoder here, okay, P. We have the noise here that is taken into account. So we need to assume some knowledge of the statistics of the noise, sorry. And we also use in the design of the precoder the combined channel matrix that involves the channels of all users but the user of interest. So that's typical of BD type precoders. Okay, solving this optimization problem yields this expression here, and at the receivers we have this kind of expression that involves the channels of the desired user, the kth user. And we have also the channels and the imperfect elements, the uncertainty that is coming in the form of the errors of the channels, the precoders that were designed, and here is the power allocation. Okay, so that's what appears at the receivers. So with this design of this rate splitting based regularized block diagonalization, that's the part that we design here. Okay, so we're going to combine this or use together these precoders with the string combiners that were described here, okay, at the users. So let's look at the numerical results. So we're going to assess the string combiners, the precoders, and power allocation techniques for a rate splitting based system with NT antennas at the base station, K users, and the K users will have MK antennas each at the devices, right? And we use these three types of stream combiners, and we're going to compare the linear zero forcing MMSC, BD, and RBD precoders. Recall that BD is basically it's the same kind of formulation of the RBD, but we basically exclude this regularization here, and then you get BD. Okay, so all of them are considered in the comparisons. And then later on, we're going to investigate the power allocation techniques. So here's the first set of results. So this is the sum rate performance of the proposed stream combiners. These curves that we have here at the bottom, they are all zero forcing, standard zero forcing precoders equipped with min-max, MRC, and MMSC combiners. As you can see, the MMSC combiners are the best ones, okay, amongst the different combiners. And at the bottom, the very worst curve is the standard zero forcing precoder without rate splitting. Okay, that's an SDMA, standard multi-user MIMO. And if you use rate splitting here, you get a gain of about up to 20%. Okay, if you use rate splitting in terms of sum rate. Now, if we change the precoders and we use BD precoders together with rate splitting, what happens? The sum rates, they increase a lot. You get to this blue set of curves here. So with very substantial gains, we're talking about gains of about 50%, just changing the precoders from standard zero forcing to block diagonalization type precoders. And again, here we have the different combiners. The standard BD with the standard multi-user MIMO, it's the worst one amongst the blue curves. So that's this the dark blue with the circle. And then if we use the rate splitting, you start to get some advantages. And if you use rate splitting with an MMSC combiner, you get even better. So you get a gain that is over 10% as compared to the standard BD. Okay, and that's the effect of the MMSC combiners. So all this was done for a scenario with 12 transmit antennas and 6 users, and each user was equipped with 2 antennas each. And here we also considered imperfect channel state information, and the variance of the error was set to 0.1. Okay. Now, a similar scenario, 12 transmit antennas, 6 users, each user equipped with 2 receive antennas, and the same level of imperfect channel state information at the transmitter was considered. And this time we're using MMSC precoders and RBD precoders, okay? Again, you see the same hierarchy in performance, and using RBD, you can see that you have the blue curves. So you have a substantial gain in sum rate performance as compared to the standard MMSC precoders. And again, you have a big advantage here, especially at high SNR, if you use MMSC combiners. They are the best combiners that we could think about. And the gains here, as you can see, is over, it's about up to 12% of gain when you use an MMSC stream combiner. And this applies to both standard MMSC precoders and the proposed RBD precoders with rate splitting. So this basically is the part that we consider the linear precoders. Now, let's look at nonlinear precoders that have the potential of increasing even more the sum rates. We consider Thomson-Harashima precoders here, and some of the details of what we did appeared in this paper here at the bottom. With the Thomson-Harashima precoders combined with rate splitting, we have the following scheme. So here we have like an encoder, message splitter, and here this is the part of the Thomson-Harashima precoder. This is the filter, the feed-forward filter used by the Thomson-Harashima precoder. Here's the feedback part, and we have here also a device that is used, a decision device used by Thomson-Harashima precoders. And here at we have the channel, and here is the receiver of the CAFE user. And as you can see, again, we have the combiners here. We have a decision device. We have SIG decoding. And then we have a combiner that is aimed to produce an estimate of the messages that were transmitted. So what happens here? In terms of the transmit signal, we consider a precoder that for the common symbols and another precoder for the private symbols. Okay. And this is the signal that will be precoded by the MT antennas. The private precoder, this part here, is obtained by this expression. So we also have a normalization factor here to ensure that the power is limited, the transmit power. And the precoder for the common stream is obtained by an LQ decomposition of the channel. Okay. And then we have here also the part of the precoder for the private streams that arises from the common one. You have the feed-forward filter, and at the receivers, we're going to have the following. We're going to have here the precoder that appears of the common stream and the channel, and here's to have the common symbol, and here they have this normalization factor beta, and the part of the precoder for the private streams. This is essentially the received vector at user K. Let's look at the numerical results of this Thomson-Harashima precoder for rate splitting based systems. We consider MT antennas here at the base station, K users, and also all the users will be equipped with MK antennas. We also consider different stream combiners. This time we only consider the min-max and the MSC stream combiners. And we also consider in the comparison linear precoders of the type MMSC with MMSC filters and RBD precoders with rate splitting and with standard multi-user MIME. So here are the results. So we have here a scenario with 12 transmit antennas, K equal to 6 users. Each user has 2 antennas, and the noise the variance of the error of the channel state information at the transmit side is set to 0.05. By the power location here amongst the common and the private streams is done by exhaustive search. Okay. And here's the set of results. At the bottom here, the bottom curve, which is this magenta, corresponds to the standard MMSC precoder with the MMSC combiner. Okay. Then the RBD precoder with rate splitting and the MMSC combiner is a bit better. So you have a gain here, which is this pink curve. They are both linear, equipped with linear precoders. They are corresponding to linear precoders. And here, the group on top, you have the Thomson-Hiroshima precoders. The black curve here, the black curve is the standard MMSC Thomson-Hiroshima precoder with standard multi-user MIMO, so no rate splitting. And if we add rate splitting and add, for example, rate splitting with MMSC combiner, we get the top curve, which is this orange curve here on top. Okay, so that's the best one using rate splitting, Thomson-Hiroshima precoding, and MMSC combining. So as you can see, the gains are up to 30% over a conventional Thomson-Hiroshima precoder with with standard multi-user MIMO. Okay, but if you compare with a standard MMSC precoder with MMSC combining, the gains are even more pronounced. You can have gains of about, let's see, from 20 bits per hertz bits per second per hertz, just over 22 to about 33. So that's a gain of about 50%, up to 50% of gain. So these are the advantages brought by Thomson-Hiroshima precoders designed together with rate splitting based systems. Okay, now moving on from the precoders and the combiners, we can describe power allocation techniques. So far, in most of the results that I've shown you, I was using exhaustive search power allocation. What do I mean by that? So that's the amount of power that is allocated to the common symbol and as compared to the private symbols. And I was assuming that the private symbols were all with uniform power allocation amongst them. Of course, you can use other strategies if you want to address, for example, different qualities of service and so on. But I was just focusing on that because of the focus was on the precoder design and the string combining. But now I consider power allocation, and I will describe what's available for us to design rate splitting based systems. We have this exhaustive search, okay, which you basically define a very fine grid, and then you search for the best possible allocation. Okay, so that's one possibility. This is extremely costly, okay, but of course works very well. And we also have probably the most well-known and most used approach, which is the iterative weighted MMSC, which uses an alternating optimization, and then you optimize the parameters of the precoders, the receiver, and the power allocation, and you update them through iterations. And you fixed, for example, 2 sets at a time, and then you optimize the third one, and then you do this in an alternating optimization fashion. This is probably the most used approach and was described in this key paper here. The trouble with this is that you need to compute matrix inversions, you need many iterations, so that's costly. And there are some other approaches like closed form approaches, and some other variations that were described in the last few years. And recently we came up with an idea that is called robust adaptive power allocation. So the idea behind this is to come up with an adaptive learning technique that is like a machine learning technique that uses a gradient descent algorithm, but incorporates statistical information of the channel state information at the transmit side imperfection. So if we have, for example, an idea or an estimate of the error variance, we can incorporate that into the algorithm and increase its robustness. So we consider the following constraint optimization problem in the formulation of this algorithm. So, and we solve this using a stochastic gradient type robust power allocation algorithm. And this has this very simple recursion. And the robust knowledge is incorporated here in this variance of the error that is incorporated here. Let me indicate this with the, I don't have the tools right here to indicate, but it's this matrix here that we have in between the P matrix of the precoders. This brings this knowledge about the error variance of the channel state information at the transmit side. And with this, we equip the algorithm with knowledge and robustness to deal with uncertainty. And the big advantage of this is the complexity is linear in the number of parameters, okay? As opposed to exponential complexity, which is the case of the exhaustive search, and cubic complexity, which is the case of the weighted MMSE approach. So with this, I can show you the computational complexity of the power allocation techniques. I measure the flops of these techniques against the number of transmit antennas, and I keep the ratio of users equal to the number of transmit antennas over 4. Okay. With this, I have the following curves. You see here on top, I have the SDMA, standard multi-user MIMO, okay, with exhaustive search, and I have the rate splitting with an exhaustive search, just the power allocation part. Okay. As you can see, the computational cost is pretty high. Then I have the second approach. It is the magenta, which is the rate splitting with the weighted MMSE approach. So you can see this is much less complex than the exhaustive search. And the bottom approach is the blue curve, which is the adaptive robust power allocation that we have described. So this is basically orders of magnitude simpler than these other existing techniques. So let's have a look now at some numerical results that show this the performance of these techniques. Here, I consider a very small system with only 4 transmit antennas, 2 users with 2 antennas each, and the error variance equal to 0.1. As you can see, the standard zero forcing precoder here, so that's the worst you could get. So there's basically no power allocation here. And then if you have some rate splitting with adaptive power allocation, so you get better, but this is This curve here is, there's no robustness included. And then if you have robustness included, you have better performance. And these two here, this is the exhaustive search. And if you take into account that the adaptive approach is orders of magnitude less complex, so you have a solution here that's a trade-off that is not too bad. And there are scenarios that you can get very close to the exhaustive search. So this is just an example. If you have a larger system, you tend to have a very close performance to the exhaustive search and also to the weighted MMSE performance. So of course, also bear in mind that we are using a stochastic gradient algorithm. So if you use a more powerful algorithm, you have the potential to get much better performance. And then the last part of the talk, we have some preliminary results on cell-free systems with rate splitting. The basic idea why we're doing this is that there's a lot of synergy between the two, because cell-free systems, they are prone to working with imperfect channel state information, and that's a case for rate splitting. Also, cell-free systems, they have this potential for improving the sum rate performance. Same thing with rate splitting, and that's why we thought that would be sensible to consider them together. So we are including, there's some archive paper that is available or will be available very soon. And the basic idea and principles I'm going to describe here. So basically, in cell-free networks, the access points communicate with all users within the network, or if you prefer to use a scalable approach within the cluster, using the same time slot. The APs, the access points or the antennas will be connected to a CPU and potentially to a cloud in order to process data and to perform precoding and power control. There'll be also exploitation of favorable propagation with channel hardening and more uniform performance across users. So this is one of the key advantages, because even with rate splitting, you can improve the sum rate performance, but the users at the border of the cells, they might experience some problems, a decrease in some rates. And if we consider cell-free approaches, because of the distributed nature of the antennas, so we can achieve a more uniform performance across users. And this is one of the key advantages. And we're addressing also key problems of cell-free systems. So we're looking at imperfect channel state information. This is, of course, at the heart of rate splitting techniques and scalability. We're going to be looking at the clusters instead of the whole network. And so the system that we are looking at considers a cluster. We have here access points that are spread over a geographic area that amounts to a cluster here. We have a number of users, K users, and each user is equipped with potentially with NK antennas. The access points might be equipped with a single antenna, with multiple antennas, but we are assuming any NT access points here. So now the difference, as before, is that you have a CPU. The CPU will do the processing. So we have K users to consider. They will have the messages, we have the message splitting, the message combining here, the encoding, and then we have the common and the private symbols that will be precoded, and all this will happen at the CPU. Then, in a very similar way to the previous description, at the users, we're going to have stream combining and SIG decoding. So I'm going to show you some numerical results with a very, very simple setting, just to illustrate the potential of this. And we're going to have matched filter precoders. We can have also zero forcing precoders. The results, they don't change too much. NT antennas or access points and K single antenna users. And the power location here employs an exhaustive search. So as you can see, the results are the following. We have here, sorry about this. We have a cluster of a cell-free network with NT access points, K equal to, here actually is 4 users. Okay, sorry about this, it's 4 users. We have the standard SDMA is denoted by the solid curves. We have here the co-located system in red with the base station. At the bottom, that's the very worst one. And in blue with the solid curves, we have the cell-free. And as you can see, there is a saturation here. As we increase the signal to noise ratio, there is a saturation in the ergodic sum rate. And this is because there is a saturation due to the variance of the error of the channel state information at the transmit side, which is set to 0.2. So there's quite a bit of uncertainty of error. And this basically makes this effect of the saturation in the curves. But with rate splitting, what we do is the following. There's no saturation. You have the red dashed curve here, which is rate splitting with a centralized base station. Okay. So you can see that the sum rate continues to grow as we increase the signal to noise ratio. And the best one is the dashed blue curve, which also is not affected by this saturation and uses rate splitting with cell-free. Okay. So that's the best performance that we get. It's roughly up to 10% of sum rate improvement as compared to a standard let's say base station with rate splitting. So if you compare the two dashed curves. Okay. So that's then I come to the conclusions of the presentation. So we have discussed the concept of rate splitting, how to design linear and nonlinear precoders, along with linear string combiners and cell-free schemes. So we considered BD and regularized BD precoders with rate splitting, and they are substantially better than other standard linear precoders. And when we consider Tomlinson-Harashima precoders with rate splitting, and we can also see a very substantial improvement in some rate performance as compared to all linear precoders. And the use of string combiners is essential for improving the sum rate when you have multiple antennas at the devices. And you can obtain improvements of up to 30% of sum rate over standard solutions that have no string combining. And they are key for any design that considers multiple antenna devices. Another, let's say, take-home, let's say, idea that I wish that you can benefit is the use of robust power allocation techniques. So this is just an initial study, but this has a lot of potential for reducing the computational cost of resource allocation in rate splitting. Rate splitting is very dependent on the allocation of resources, and the available solutions that we have are costly. So anything we can do to reduce the computational cost and to make the resource allocation also robust, I think is beneficial and can be considered in the future. And at last, cell-free schemes with rate splitting. We have shown some preliminary results, and we have shown that they can obtain very significant gains over centralized approaches. And that basically concludes the talk, and some ideas for future work, and something that we have been looking at include other cell-free designs inspired by rate splitting. So we're working on that at the moment. Iterative detection and decoding schemes with rate splitting. Also, something that hasn't been considered yet is basically the use of nonlinear string combiners. So this has the potential also to improve the performance, and the use of intelligent reflective surfaces with rate splitting, and more powerful optimization algorithms for large-scale systems with robust elements. So that concludes my presentation. So I hope that you have enjoyed it.
Thank you, Rodrigo, for a very interesting talk. And I fully agree that low complexity precoder and power allocation will be a very, very important research direction in the implementation of the rate splitting. Okay, so we have received multiple questions. The first one is on the numerical results. So the question is whether the results are analytical or the simulation.
Well, all these results are by simulation.
Yeah.
So what we have done involves, let's say, some analytical expressions. For example, these are coming from what we obtained here for SINR expressions. These are not analytical, okay? But the ergodic sum rate results are all obtained by simulations.
Yeah, and we also have another question. I guess this question is popped out when you mentioned about the power allocation scheme for imperfect CSIT scenario. And the question is on a specific symbol with circle, a circle with a point inside. So I guess the question is related to an unclear symbol.
Let me see which one. Can you tell me his typing?
I guess it's maybe previous slide. Let me recall myself. No, it's at the bottom. So when you're discussing the power allocation scheme for the imperfect CSIT, the statistical, the robust precoder, power allocation scheme.
Ah, okay.
Yes, I guess it lies. Yeah.
This one, you mean is the Schuh-Hadamard operator?
Yeah, this is
yeah,
operator that maybe you can.
Yeah, this is a mathematical operator, the Schuh-Hadamard operation. So we use that in the constraint here.
Yeah. Okay, so another question is on what were the major issues related to the rate splitting schemes you implemented?
I think the difficulties we have are, for example, with large scale systems, because of the power allocation. So if we want to compare, for example, the power allocation using like the weighted MMSE approach, the exhaustive search and others, if you have a very large systems, this is very, very time consuming. So that's why we have considered smaller systems. See, so when we started to do this, we started to work on this. We had a lot of difficulty to go to larger systems. So we would need a very powerful server to run the simulations, and I think this motivated the development of these adaptive approaches, because then it's kind of linear complexity. And then you can see, for example, the difference in flops. And with these algorithms, we can go to large scale systems with over 100 antennas and so on without problems. I think this might be a nice venue for future work.
Yeah.
To further develop more algorithms for resource allocation for rate splitting, because they are key. Without this resource allocation, you don't have the gains. And the available solutions are relatively costly. So this seems to me like a good way forward.
Yeah, I fully agree that I think the major issue here is that rate splitting is sensitive to the power allocated between the common and the private part. So this allocation is a very essential problem to rate splitting. Okay, we also have a question on, is there a big difference on results with perfect CSI and imperfect CSI?
Yeah, that's a good question. Yeah, I don't have here in this set of slides the results with perfect CSI, but perfect CSI favors the standard SDMA, standard multi-user MIMO. So the gains of rate splitting are less pronounced, but you still have gains in most of the scenarios that we have considered here.
Mm-hmm. Well, actually, I also have a question related to all the power, because you consider imperfect CSIT scenario, and all the precoder, like a regularized block diagonalization or other precoders that you design are based on the channel estimate, the instantaneous channel estimate at the transmitter, or based on the ergodic scenario that based on the statistic of the imperfect CSI.
Yeah, this is, let me see. Try to check here if I think I remember no, I think this is the instantaneous CSIT, but that we have the variance of the error. So we could infer the variance of the error. And
yeah, because the variance of the error that you set at this moment is 0.1 or 0.05, right? So they are relatively small. So I'm curious that if the variance increases, like a severe imperfect CSIT scenario, how will those precoder schemes be influenced?
I think I might be able to show something, because it's in the paper. We have that. We have a scenario. Just a minute, I can. Just a minute. I'm gonna dig the paper here.
Oh, no worries. Yeah.
Yeah, I can show you the.
Yeah, that's fine. Maybe I can go back to check the paper.
No, that's fine. I can show the figure of the paper that shows the impact of this variance of the error.
Mm-hmm.
I got it here. Just let me just change the share. Change the way it's shared. Yeah, I think you can see that, right?
Yes.
Here. You see, so we varied here the variance of the error from 0.02 to 0.1. 0.1 is quite a bit of a and as you can see, it still is, it resists, and you still have very clear gains.
Yeah.
Now, your question is very interesting because we were talking about MMSE filters, and also the regularized block diagonalization has a regularization. And every time you have regularization, there is a bit of robustness. So if we show this kind of result, if we consider zero forcing type filters, you will lose more when the uncertainty increases. So, but you can withstand quite a big, a great deal of uncertainty. You see, yeah. But you lose. You see, if you lose, for example, in the best performance, you lose. You go from almost 40 bits per second per hertz. You lose to you get to below 25. So it's a loss of maybe a 35–40%.
Yes.
Yeah, when you increase this.
Yeah. Thank you. Yeah, and I'm also curious on the last figure that you illustrated. Not last, the cell-free results, because that's quite a huge gain when rate splitting is introduced, but it's in an underloaded setting for NT equal to 8, and we have 4 users.
Yeah. Here should be 4 users. I'm sorry.
Yeah, yes, 4 users. So in such scenario, I'm curious why rate splitting can expect quite a large improvement.
Yeah, I think the improvement of rate splitting in general is because of the saturation due to the error that we have here in CSIT. So there's no saturation. This is kind of what was expected, right? But the gain, which is the dashed blue curve over the dashed red curve, this is, both of them are rate splitting, and the gain is about 10%. Which is due to the distributed antennas. So basically just, distributing the access points, and you have basically a reduced distance from every antenna to every user. This already provides a gain. And of course, here you have the propagation effects of a base station, that even with rate splitting as a base station, you have the propagation effect. So some users are distributed in the cluster, and they suffer more significantly from the propagation effect, especially users that are farther away.
I see. Okay, so one last question is from the chat box, is that how was your SIC receiver implemented? Which signal will be first canceled?
Okay, this is a bit different from successive interference cancellation done in other contexts. With rate splitting, we do one stage of SIG only. So we only remove the the common symbol. So if we go to that slide, I think this one is best for. So you see, we are only interested in removing the contribution of the common symbol. Okay, so only one stage of successive interference cancellation for each user.
Yeah, okay. I think this is a standard question on rate splitting that we call, in rate splitting, there's no decoding other things. So we always first decode the common string and then use SIC to remove it and then decode the private strings. So this is for one layer rate splitting. Okay, so if there's no other question, I will end the webinar today. Thank you, Rodrigo, again for your interesting talk, and thank you all for attending this webinar. And a quick reminder that our 7th webinar will be held on December 14. So it's 14 days later, and it's a Tuesday of the week after next week, and the same day as today. And the talk will be given by Professor Carlos Mosquera from University of Vigo. And you can go to our webinar website for more information. Okay, looking forward to seeing you next week, the week after next week. Okay, thank you, Rodrigo.
Thank you, my pleasure.